Welcome everyone to our starting of the new chapter, which is laws of motion. So, with this new chapter, we'll be diving into a lot of new concepts and a lot of ideas which we have been knowing all along already. Mainly, we'll be covering the ideas of Newton's laws of motion and that how forces act on blocks and pulleys. What are the different kinds of forces when we categorize them on the basis of their nature, or whether we categorize on the basis of in which direction or by what bodies are they applied. For example, we want to consider tension. So tension force, normal force, they will be categorized in some different aspects, and for example gravitational force and electromagnetic force, they will be categorized in different bases. So what are some examples of forces? Some examples can be, let's say there is a pencil box kept on a table, and when you push that pencil box on a relatively smooth table, then the pencil box would actually accelerate on it. It would start gaining speed. So this is what is meant by applying a force on a body. And one more example can be a branch of a tree swaying in the wind. When the wind is moving in air, the particles of the wind interact with the leaves and branches of the tree, and they exert a force on it, which causes the branches to move and sway. So from this we learn the idea that when two bodies come in contact, or when some body is pushed by being in contact with it, then we can exert some force on it. Like in the case of tree and branches, the air pushed the branches and it exerted some force. One example can be the example of Earth and Moon, where Earth exerts a force on Moon which keeps it going in a circular motion around Earth. Now we know that this force is gravitational force, and the thing which we notice that is that there is no contact between Earth and Moon for Earth to exert a gravitational force on Moon. So we can say that there is no need for contact to exert a force in this case. So from this we can say that the contact between two bodies is not necessary for forces to act on one another. What is a compact definition of a force? Force can be defined as interaction between two objects. One of the smallest definitions. What is a force? The SI unit of force. The SI unit of force is 1 Newton, that we already know, represented as 1 N. Force is a vector quantity. Since it has a magnitude as well as direction, it can be added using vector addition. And now we are going to group the forces in various groups. So the first group, for the first kind of force which we will be learning about, is gravitational force. Now we already know what gravitational force is. If there are two masses m1 and m2 which are kept at distance r from each other, then the gravitational force, which is attractive gravitational force between the two masses, is given by g m1 m2 upon r square. Now this force is commonly known as now this law is also commonly referred to as inverse square law, as the gravitational force is inversely proportional to the square of the distance between these two masses. Now we are concerned with the gravitational force on some small bodies by Earth in this chapter, which is laws of motion. So if you have Earth and there is a body on Earth, let's say this is some block resting on Earth, then the gravitational force between the Earth and the body would be capital G, mass of Earth, let's say capital M, mass of small block, that is small m, and the distance between the block and the center of Earth, that is some r. And this particular distance, let's say this distance is some r. So this distance would be radius of Earth, and we would say that G capital M small m upon r square. This force is the attractive force between these two bodies. And since all bodies fall towards the center of Earth, the force would be acting vertically downward direction. We know that what is the value of G, the gravitational constant. So the value of gravitational constant is some 6.67 into 10 to the power minus 11 Newton meter square per kg square. And the distance between the bodies and the particle would be basically radius of Earth. So r is the radius of Earth, and the interesting part comes now, that what is gm by r square. So this value gm by r square has a dimension of acceleration, so we write it as small g. This is called acceleration due to gravity, a term which we are familiar with. So this is relevant to us as we are mainly concerned with systems which are acting near Earth. So small g, this is action gravity, and its value we know as 9.8 meter per second square. So this force acts on the mass m and acts towards the center of Earth. And if we were to replace this particular form gm by r square with the value g, then we would get the gravitational force exerted by Earth on a mass m is simply mass of the body into this value, which is g, where g is action due to gravity. So this is the gravitational force acting on a body in vertical downwards direction. So this is something which we have an idea about, right? We have an idea that the gravitational force acting on a mass m is mg. So let's move ahead. Let us talk about gravitational forces. So electromagnetic forces. Electromagnetic force, will be talking about what is the force on two charges q1 q2 when they are at rest with respect to each other and are at rest with respect to the observer seeing these two charges. So the electrostatic force between these two charges has a value 1 upon 4 pi epsilon naught into q1 q2 by r square. So one by one we'll go through what we are trying to say. So this value F, this is the electromagnetic force, or we can say this is the electrostatic force in this case. Electrostatic force, why? Because the charges are at rest with respect to the observer and with respect to each other. So this is an electrostatic force. This whole law is called Coulomb's law, and this constant epsilon naught is called the permittivity of vacuum. Permittivity of vacuum. So as we see, this force F is also an inverse square law. It is inversely proportional to the square of the distance between the two charges, and this was also the case with gravitational force. The gravitational force was G m1 m2 upon r square, and that force also is inversely proportional to distance between the masses. Now charge and mass are two properties of the same bodies of matter, and the mass aspect of that body interact with each other with this particular equation gm1 m2 by r square. So these two laws are kind of similar, right? Both are inverse square law, but yet these two laws cannot be reconciled. That is, they cannot be unified as of now, and this is the reason behind that is one of the reasons behind that is that these two the forces between two masses m1 m2 or the gravitational force in general is an attractive force, while the electromagnetic force is a repulsive as well as attractive force. So let us move on to next part. So, well, as we are seeing that although we are covering each force in quite detail, but that is not what is the objective of this chapter is. We are going through some light introduction that what are the basic nature of the forces, like I said, and we are trying to categorize them. But mainly we want to move to the next part where the questions come from. But still, we want to know, okay, what are the nature of forces? So, like, what is a strong nuclear force, which is the third kind of force? Nuclear force acts between the nucleus within the nucleus. Let's say this red part represents the nucleus, and within the nucleus, you have some neutrons and you have some protons. So, the protons would be repelling each other with some electrostatic force. So, what is keeping them binded inside the nucleus? So we said that the strong nuclear force is the one responsible for keeping them attracted towards each other. So the nuclear force or the strong nuclear force is the force which acts between each pair. So each pair is exerting a force on each other, and this force acts at very small distances, that is 0.8 fermimeter to 3 fermimeter. 0.8 fermimeter to 3 fermimeter. The forces act at very small distances with respect to each other, and we can say that like we are saying that the forces acting between neutron and proton, they act at very small distance, that is 3 fermimeter. And what is 1 fermimeter, for example, is like 10 to the power minus 15 meters, which is very small distance. So once the proton is out of or neutron is out of the nucleus, these forces practically become zero. But within the nucleus, they are strong enough to overcome the electromagnetic force multiple times. So like it is said here, the nuclear force are 137 times as strong as the electromagnetic force. Mainly these forces or these forces are attractive in nature, attractive force between nucleons, and like we said, the repulsion force between these two protons would be 1 by 4 pi epsilon naught E into E. Let's say the distance between them is some r squared. So this distance, this force between the protons would be some value, but the strong nuclear force is far stronger than the electrostatic force. And additionally, it is given that it also holds the quarks within the protons and neutrons close to each other, and that is, it acts even inside protons and electrons. Interaction between subatomic particles responsible for decay of nucleus. So we say that when we talk about weak nuclear force, the weak nuclear force is responsible for decay of the nucleus. It acts at very short range, that is 10 to the power minus 18 meters. So this was the part in which we covered the types of forces, that is the electromagnetic force, Before that, we covered gravitational force, strong nuclear force, and weak forces. So weak forces, which we are saying, is that they are responsible for the decay of the nucleus and act at a distance of 10 to the power minus 80 meter. So with this introductory part of the lecture complete, next we'll be jumping on to the Newton's laws of motion and what is it, or what are their relevance in real life situations. So thank you for joining in this lecture, and have a nice day.